I'm talking now about IR. Good. So this spectroscopy lecture is going to focus on infrared or IR spectroscopy, which is often used in partnership with GCMS, proton NMR, or carbon NMR to do structure determinations. It can be, but is probably seldom used to do structure determinations by itself. IR spectroscopy is the result of the vibrations, stretches, and bends of atoms within a molecule. In a very simplistic sense, we can think of a chemical bond between two atoms as being somewhat like a spring and obeying Hooke's law and having a frequency of vibration. We can actually use electromagnetic radiation to manipulate those vibrations, which is where IR spectroscopy occurs. These vibrations, animated here for the water molecule, are very simple with a small molecule. They're a little bit more complicated with larger structures. There are two symmetric and asymmetric stretches for the water molecule shown on the left. And there's a bending scissors type mode shown for the water molecule on the right. These are the normal modes of vibration for water. You're going to see a lot more of these types of vibrations in this talk. In general, the IR experiment works by exciting one of these vibrations and having an absorption of a photon as a result. If the frequency of light is matching the frequency of the vibration, we can excite a vibration to a higher quantum state of vibration, and we can see an absorption in the IR spectrum that results from that. Since we're treating bonds as if they're springs, we can think about Hooke's law and what we know from physics about the way in which springs vibrate. And in general, the two things we're going to care about are the force constant in Hooke's law and this mass term involving the mass on each end of the spring. As we go from carbon singly bonded to carbon triply bonded, we're not manipulating the mass at each end of the spring. That's remaining constant, so this term isn't changing. What does change is the force constant, which is roughly related to the bond strength. The longer carbon-carbon sigma bond has a smaller bond order and is not connected by a bond of equal strength to that of the carbon-carbon triple bond, which is shorter, has a higher bond order, a greater bond strength. And what we see is that as the bond strength goes up, so does the frequency of the vibration. As K increases, so does the vibrational energy. And in general, in IR spectra, we see triply bonded stretches further to higher frequency than we see those of singly bonded species, as long as we're talking about the same two atoms on each end of that bond. We can also see bond strength differences looking at hybridization. A carbon with different hybridization will have different bond energies connected to the same hydrogen atom. A carbon that is sp hybridized will form a stronger bond to the hydrogen that's connected to it. And as a result, we see a vibration at higher frequency or higher energy. That is a result of the fact that the bond used by the carbon, the sp orbital, is of lower energy than the orbital used to make the bond in an sp3 hybridized carbon atom. The change is much smaller here when we're looking at the effect of hybridization, but we're going to see separate signals for sp2 hybridized carbons attached to hydrogen and sp3 hybridized carbons attached to hydrogen in a couple of spectra today. Something that we don't often care about in the context of Chem 344, but is a real issue, is that isotopic substitution changes the mass term quite a bit. And as a result, substituting a hydrogen for a deuterium causes a big change in the absorption frequency in the IR spectrum for the same type of chemical bond. This is a sample spectrum here for butanone. We have some absorption features here running from about 4,000 wave numbers all the way down to 5,000 wave numbers. Some of these are very diagnostic and we're going to pay attention to. Others we're going to ignore and are going to be a little bit less useful to us. The scale here on the left is in percent transmittance. Sometimes it can be in absorbance. Oftentimes, and in all the spectra you'll collect in Chem 344, they will be in percent transmittance. And the horizontal axis here will be in wave number or inverse centimeter units. In NMR and carbon and proton, all of the peaks are going up from a baseline at the bottom. In the case of percent transmittance IR, all of the peaks are features that are coming downward from a baseline across the top of the spectrum. And so it's important to notice that these downward aimed peaks are the absorption features. And we're also going to care, as we look at these spectra, that there are regions where there's no significant absorption. So the presence of these downward aimed peaks gives us some information in those regions. The lack of any peaks in that region also gives us some good information. And so for the same spectrum of butanone, we can see on the far left a region that is usually reserved for single bond stretches. In this case, there are only CH stretches in this molecule, and they pile up right here at about 3,000 wave numbers. This video down here shows an example of one of those stretches. Moving to lower frequency, we'll see some different types of bonds in their stretches. The triple bond stretching region is largely empty for a molecule like butanone, which makes good sense because there are no actual triple bonds in the molecule. As we move further into the double bonding region, we see a really, really intense feature here for the CO double bond. This is pretty common for a carbonyl group to have a very intense stretch in this region, and is often used as a diagnostic for having carbonyl groups in a molecule. As I said before, triply bonded structures are at higher energy, double bonded structures are at slightly lower energy, and as we move from this double bonding region to the right, we'll get to a lower energy single bonding region. And in this region, we see a lot of stretches between singly bonded atoms. We also start to see some other types of motions, some bends and some scissors type motions. In this case, we have a CC stretch between the carbons attached to the carbonyl carbon. And far out to the right, we have a bunch of low energy vibrations, a lot of scissors motions. CH bends will be in this region. If there's an aromatic molecule, the out-of-plane bending vibrations of the ring itself usually show up in this region. In this spectrum, I think the most important features to pay attention to are the sort of intense carbon-hydrogen stretching feature right here, which corresponds to carbons that are sp3 hybridized with hydrogens attached, and this really intense carbonyl stretch, which is usually really good for identifying carbonyl-containing functional groups. This spectrum is a little bit more boring. You can see in this region over here, there's not nearly the structure we saw with the ketone on the previous slide. This is for heptane and is a simple alkane. And as a result, it has a fairly boring and pretty simple IR spectrum. On the far left, we see that similar deep feature at 3,000 wave numbers, which corresponds to a number of different CH stretches in the molecule. There's not a whole lot in between because there are no triple bonds or double bonds. But then down in the fingerprint region over here, we see a lot of other CH bends. This region of the spectrum below 1500 is usually too complicated for the simple sorts of analysis that we're going to do in Chem 344, and we're not going to use it all that much. I'd like to compare this heptane spectrum to that of heptene. So I've overlaid the heptane spectrum in red over the 1-heptene spectrum in black. And so here's 1-heptene, here's the two of them together. You can see the changes by simply converting the alkane to an alkene. There is a growth of a new feature right here, a couple of new features right there, and some pretty intense ones in this region. Using some computational chemistry, we can model those stretches and bends and see what the changes are that resulted in them. The most obvious is probably right here. We had all carbon sp3 hybridized H stretches in heptane. By putting a double bond in the molecule, we introduced some sp2 hybridized carbon H stretches, and as a result, we see this new feature right there corresponding to that CH stretch of an sp2 carbon. We also have introduced a new carbon-carbon double bond in the molecule, and in our double bonding region, we see a strong feature there. It's important to note that this is actually a little bit weaker of a feature than we saw with the carbonyl stretch. The more different the two atoms are attached to a bond, the more intense that feature tends to be. And so in general, we'd expect a carbon-oxygen double bond to have a greater intensity than a carbon-carbon double bond. And it's important to distinguish between the intensity of signals and the integration we use with proton NMR to determine how many of those atoms or molecules are making that signal, to with IR, where the intensity doesn't tell us how many molecules or parts of the molecule are making that signal. What it tells us is something about the asymmetry of the atoms involved in that bond. And so here we see a moderate intensity because we have carbons on each end of that double bond. Here we see some out-of-plane bends of the hydrogens attached to that, each of those CH stretches attached to the alkene group on the end. And there's another set of those right there, and you can see those hydrogens kind of wagging on the end of the molecule. And so the introduction of these sp2 hybridized carbon gives rise to a number of new stretches. When we get to an alcohol, we see an entirely new type of structure here. We see this very, very broad and very intense signal. This is characteristic of an OH in a molecule, but not only an OH in a molecule, specifically an OH in a molecule that is hydrogen bonded to other molecules in solution. The intensity of this and the broadness is indicative of that OH hydrogen bonding. In the gas phase, this OH signal is much, much smaller. If you diluted this alcohol in another solvent, we would also see the intensity decrease as those individual molecules were isolated and not hydrogen bonding as effectively. We can see the sp2 hybridized carbon H stretch right here is an intense feature on the side of that OH stretch. Next to it, we have the same CH stretches that we had from sp3 hybridized carbons. Additionally, we've got a carbon-carbon double bond in this molecule, so that should be this feature right here, again of moderate intensity, and we can indeed see that that's the CC stretch. So important from this line is this idea of hydrogen-bonded OHs being very broad and very intense, and a good way to identify OHs or alcohol groups in a molecule. When we look at hexynes, we've now changed things a little bit further. We now have sp hybridized carbons bonding potentially to hydrogen atoms. And in the case of 1-hexyne, that's exactly what we see. And I want to draw your attention to this highlighted signal right here, which is at higher frequency than we saw for the sp2 hybridized carbon attached to an H and the sp3 hybridized carbon attached to an H. And we also see that it is of a pretty big intensity. And that results from the asymmetry between the light hydrogen on one end and the heavier carbon on the other. and that CH stretch is present right there. We have another new feature in the middle of the spectrum. This is the first time we have a stretch in the triple bond region, and that corresponds to the CC triple bond stretch found in 1-hexyne. All of these features in the fingerprint region we're not going to worry about too much. These are what I would consider the two most important stretches to pay attention to. In addition, we still have the sp3 hybridized carbon hydrogen stretch. When we go to 2-hexyne, this triple bond stretch becomes of very low intensity. And this is an important point about IR spectroscopy that I mentioned earlier. The intensity of these signals is in large part based on what atoms are attached and how similar or different they are from each other. In this case, we have carbons on each side of that triple bond which are similar, and we have a methyl group attached to one and a propyl group attached to the other. As a result, the intensity is rather small for this transition. And in fact, if we go one step further and move the triple bond from the 1 position to the 2 position, all the way to the 3 position, which is at the center of the molecule, the CC stretch intensity goes to 0. And that results because the two sides of that triple bond are symmetric. They are both carbon atoms with ethyl groups attached. And as a result, the change in the dipole moment as that vibration occurs goes away, as does the intensity of that transition. So the important thing to remember here is that sometimes the absence of a particular stretching feature in the IR spectrum doesn't actually mean the absence of that structure in the molecule itself. All three of these structures have triple bonds, and the intensity of that signal changes greatly depending on how that triple bond is substituted. So for symmetric bonds, there may be little to no intensity for their absorptions. To summarize a lot of what I just said, I want to talk about the different types of things you should be looking for in the IR spectrum based on the frequency range. Our bonds to hydrogens tend to happen at pretty high frequency, and we saw some examples of CH stretches and OH stretches that were higher than 2800. The OH stretch in particular we saw is a very broad and deep feature. The triple bond region is sort of in the middle, and we saw an example of a number of CC triple bond stretches. Then we have our double bond stretching region at lower frequency. CO stretches tend to be very intense. CC stretches a little bit less so. All of this information is great for determining the functional groups present in the molecule and giving you some idea of how those atoms are connected in the molecule. Slightly less useful in most cases is this fingerprint or CH bending region. For the purposes of 344, we're going to largely ignore those. The last thing I want to draw our attention to is this double bond region, which not only can tell you by the intensity of the signal that it's probably a carbon-oxygen double bond, but the location or frequency of that signal actually is often used to identify exactly which type of carbonyl compound this might be. And we can do that by having a bunch of previously determined typical regions based on what functional group created them. These are all experimentally determined or empirical observations. None of these values is absolutely representative of all stretches for that functional group, but often pretty close. We have ethyl acetate over here on the right and its IR spectrum. There's a really intense signal in the double bond region at 1743 wave numbers, which corresponds very well to the standard 1740 of a carbonyl stretch for an ester, and so that fits with the pattern. And likewise, for an amide or a ketone, we can use the location of that stretch to give us some insight into the likelihood of this molecule being an amide, or in this case, this molecule being a ketone. I definitely want to emphasize that none of these values are perfect and encompass all possible ketones or all possible acid chlorides, but you can see that there's a pretty big difference between an acid chloride and an aldehyde or a ketone, and so we can use these values as good indicators of what particular functional group might be present. The commonality of all three of these is that the signals are really intense. And again, that has to do with the fact that one of those atoms is a carbon and the other is an oxygen, and there is a big change in the dipole as that vibration occurs, resulting in a pretty big intensity. So I want to talk through about 4 examples of some spectra and what you should see in them if you don't know what the molecule is. This first region on the far right is the fingerprint region, and we're going to sort of ignore and not worry about too much. This is the big feature in this spectrum that I think is useful. It's in the triple bond region, and so it tells us there's probably a CC triple bond or a CN triple bond in the molecule, and we can actually go one step further. This is almost certainly a CN triple bond. This is a really, really intense stretch for this region, and the intensity of it indicates that we probably have an asymmetry in terms of the 2 atoms attached to that triple bond. Over here we've got some hydrogens that must be attached to sp3 hybridized carbons to produce this stretching feature as well. We don't see any evidence of any sort of CO double bond or CC double bond stretch, and that region is pretty empty. We don't see any OH or NH stretch evidence, so we can probably say that this molecule has a cyanofunctional group. And in fact, this is a IR spectrum of a 3-carbon nitrile, which only has the cyanofunctional group in it. This spectrum is much, much more complicated in the fingerprint region. Again, we have our carbon-hydrogen stretches at 3,000, and that's a common feature of most alkanes, not often helpful in making determinations of structure. We do see a really intense feature here in our double bond region. And in fact, we see a couple of different intense stretches in that double bond region. Both of these happen to be CC stretches. We don't see any evidence of a CO stretch at higher frequency. We don't see any sort of evidence of a CC triple bond or a CN triple bond. There's no evidence of an OH or an NH, so it's not surprising that this IR spectrum fits the molecule anisole, where we've got a couple of different types of aromatic CC double bond stretches and a lot of single bond stretches to CO, CO, a bunch of CH stretches there, and some sp2 hybridized CH stretches as well. This is a much simpler spectrum than the last one, where our big feature is really this typical alkyl signal at 3,000, where we have hydrogens attached to sp3 hybridized carbons. There's very little happening in the fingerprint region even. This is a similar spectrum to what we saw earlier with the straight chain alkanes. So this is probably a molecule without a whole lot of functional groups attached to it. There's definitely no CO or CC stretches, no triple bond stretches, nothing in our OH or NH region. This is 2,3-dimethyl-2-butene. This is a good reminder that while we don't see any CC double bond stretch, that doesn't necessarily mean there isn't one in the molecule. And this is another one of those examples of the symmetry on both sides of the atoms involved in the stretch, reducing, or in this case, removing the intensity of that signal. And so even though there is a CC double bond, that symmetry makes it not observable in the IR spectrum. This is a great example coming out of the McMahon Research Group here at UW. where you actually can assign all of the fingerprint region, although it uses a computational approach that is way beyond the scope of 344. I did want to show you one example where that region was actually assigned. All of these stick signals here are the computational prediction of various vibrational modes, and the experimental spectrum in black matches very well to those predictions. This is actually a mixture of two different conformational isomers, the sin-sin CON6 molecule and the sin-anti-CON6 molecule. IR can be used in this fingerprint region. It can be used to identify these structures, but requires some pretty big computational effort in order to match them. These calculations were done at a very high level of theory and basis set. But one of the neat things that IR can do is actually show the difference between two different conformational isomers of the same molecule. And so this is an example of how IR is used experimentally by organic chemists. And this is also another one of those examples. And this is again coming out of the McMahon group. This is a slightly different application of IR spectroscopy. This is actually IR spectroscopy used to follow a chemical reaction. And it's one that NMR, both the proton and the carbon NMR, would not be particularly useful for, because this reaction needs to happen at about 10 Kelvin. This is kept very, very cold. That's minus 263 degrees Celsius, so it's not really amenable to putting in an NMR spectrometer. In addition, all of these carbons are going to be fairly similar in chemical shift, except these two in the reactant, which are sp3 hybridized. And depending on which product is formed, possibly one or fewer of the carbons in the product are sp3 hybridized. This reaction involves photochemistry, or shining light on a precursor to form one of these species. This diazo compound has a nitrogen group on it, and by irradiating it, you can knock the nitrogen molecule off as nitrogen gas, which could leave a carbene, or perhaps that molecule would rearrange into this species, or possibly ring open into one of these where a carbene or an allene structure are in the ring. These are all pretty strange molecules that are certainly deficient of a lot of hydrogens, which is why this reaction was done at such a cold temperature. IR spectroscopy was actually used to confirm the identity of the product in this case, which is a pretty neat application. So this is a subtraction spectrum and a fairly complicated IR application, but it can be understood pretty simply. Down at the bottom in blue is a predicted spectrum of the reagent, and you can see that there are peaks up above aimed downward that match pretty well to the predicted spectrum below. All of these peaks aimed downward on the experimental spectrum in the middle are those that went away as the reaction occurred. And so this is the way that the folks involved confirmed that the reagent, after irradiation, disappeared by those downward aimed peaks. Every peak that's aimed upward on the experimental spectrum is something that grew in after irradiation. And as you can see, there's a whole lot of new IR features that appeared, and those all come from the product, which in this case is the allene type structure up here. And you can see really nice matching between these features. And this was taken as confirmation that the reaction was successful, and the diazo compound lost nitrogen and formed this allene product. This type of organic chemistry couldn't be done without both computational tools as well as a good understanding of IR spectroscopy. What we're going to do in 344 is not nearly that complicated. We're really going to focus, as I mentioned earlier, upon identifying a few key functional groups. We're going to remember that the frequency of absorption of all of these functional groups is dependent on the bond strength between the atoms involved and the masses of those atoms. There are certainly going to be IR stretching frequencies of varying intensity. The most intense ones we're going to see are usually going to be carbonyl stretches, and we're going to use those to identify carbonyl functional groups by their frequency. And remember, most of the spectrum below 1500 wave numbers we're going to ignore for Chem 344, but as I showed you on a slide just one ago, those can be analyzed by using some computational tools, but for our purposes, we're going to focus on the functional groups that are easier to identify. We'll stop there.